So, good evening, and thank you for joining us this evening for our tech talk, our second tech talk in Finding Water series. I'm Angus Armstrong. I organise the tech talks for CED, and if you're not already on our mailing list, then drop me an email and you can be added to it. If you emailed me at techtalks@ced.org.uk, we can add you in. If you want to find out more about CED, then if you go to the ced.org.uk website. All of our talks will be available on CED's website and on our YouTube channel shortly after the talk. We're super pleased to see Malcolm Anderson back tonight. Thank you very much, Malcolm. He's returning to speak to us this evening and share his knowledge and experience relating to geophysics, how to select a method, and what is available locally and what it will tell us. So I will hand over to Malcolm and he will run the presentation. Is everybody else muted? Okay, Malcolm, over to you.
Thank you, Angus. Good evening, everyone. And hopefully you can see the presentation.
Yes.
So if you can all see that, we'll make a start. So as Angus explained, this talk is the second one of the series. And so whereas the first talk was essentially covering the desk study stage, this second one is the survey stage, of which I'm going to primarily focus on the geophysics surveys and how to select a suitable method, what's available, and what those surveys will tell you. Essentially, there will be a third one, which will then be the well and borehole design, construction, and testing. And the main focus of this talk is going to be examples from East Africa and the main relevance as the small-scale water supplies for the sake of argument, 500 persons. So that will be schools, hospitals, villages, hamlets, and homes. So those are the core areas that CED works on. Obviously, it's unsuitable for anything larger than that and more commercial, but that's where my work is. So if anybody has those kind of problems and issues, then by all means, give me a call. Before I get into it, there is a very useful reference on this topic, which is an introduction to geophysical exploration, written by Phil Keary and Mike Brooks. I'm showing my age a bit here because I had the first edition, and Phil Keary was my tutor at university. Sadly, he passed many years ago, and he was a brother in the Lord, and so go and buy his book and bless his family. So that's a good book to look up if you want to see the full engineering details behind geophysics. It's a very good introduction to how and he takes it very gently, so that even if you don't have a background in geology or even groundwater, it's very accessible. So the talk today is just going to have an introduction with the current preamble and some basics. I'm then going to talk about the water feature survey, which essentially is the site investigation component of the desk study. Level surveys, which will be very familiar to all of you. So I'm not going to speak very much on level surveys, other than just to mention that there's a natural grouping of the geophysical surveys, level surveys, and water feature surveys. So they are often done together. Then I'm going to talk about the geophysical surveys themselves, how to plan them, an overview of each of the main geophysical survey methods, and some common practical examples. And then we're going to close with the conclusions. So let's start with the basics. And as I mentioned in my previous talk, the opportunity to save cost reduces as the engineering value chain advances, which means that the main opportunities to save costs are in the desk study stage and in the site investigational, as in our parlance, the survey stage. And then as you get down to design, construction, operation, the opportunity to save money becomes less and less. So the survey, the context of the surveys is very important because it basically decides how the water supply for the next 20 to 50 years is going to be set up. So there's appropriate thought at this stage is very important because that then leads into the design and what is actually built. So it is a very key stage in the decision matrix. And there's a nice arrow to show that you've got your reduced cost savings advancing as your project follows through that engineering value chain. So the site investigation process, most of you will be very familiar with. So once you get to this stage, you review your desk study. And as I said, you carry out your surveys, of which the first one is the water feature survey, which we'll talk about in a moment. Identify suitable geophysical methods, sites, and associated costs. Design and undertake those selected geophysical surveys, undertake your level surveys, and then that all then leads into the borehole design, construction, and testing, which is the next talk. So let's start with the water feature survey. And essentially what this is an investigation of all the water features you can find on your topographic map that's in the area of your interest. And the purpose here is to make sure that the information you see on the ground is the same as what you see on the map, because certainly if you have a topographic map which goes back to the colonial era, then it's going to be 50 or 60 years out of date, and the groundwater levels may have gone down, the water levels may have gone down in general. So you may have the spring lines may be at different levels than they were at that time. Fortunately, groundwater doesn't change too much, and so most of the time it will be the same. But if there's been a lot of borehole extraction, then the groundwater levels will have gone down and the springs will have dried up. So the water feature survey essentially goes around assessing and inspecting those features to make sure that the map information that you've used at the desk study is correct. And that includes the evaluating the water levels and depths of the rivers, springs, lakes, boreholes, wells, and anything else that is related to the groundwater system. And since you're going there in person, you got the opportunity to take some water quality measurements, which is what my colleague Hanok is doing here. He's got a water quality probe that's going to measure the physical chemistry. That's the electrical conductivity and the pH, temperature, and dissolved oxygen of the water, which tells you a lot about whether the water is come from rainfall and is basically near surface water, or whether it's coming from depth, in which case the components like the ORP and the EAE, electrical conductivity, will be higher. Another very important task is to canvass local opinion. Usually the locals know a fair amount about their water supply and what's available, and if there's any misinformation in your desk study, they'll be happy to put you straight. So questions to ask are: what has been missed? What water is preferred? And then verify the desk study and revise the conceptual model that you established at the desk study stage. And that's essentially it. That's a water feature survey. So there's no point in spending too much time on it. I think most of that is self-evident engineering work. In the process, there are a number of questions to keep in the back of your mind that the water feature survey will help clarify. And basically it says, are there more reliable aquifer targets nearby? As I mentioned in the first talk, most of the time the demand location governs where you want to put your well or borehole. Because wells and boreholes are not constrained by river topography, you can most of the time put them wherever you want, and therefore the best location is right next to the demand. There are limits to that. The local aquifers at the location of the demand may be inappropriate or unsuitable, in which case you're going to have to spread your gaze a little bit further. So one of the questions is, are there more reliable aquifer targets nearby where you're going to be able to get a better water supply, and then is it worth that pipe cost? And then Other questions: what is the well capacity and the quality likely to be at each location? Which of the target options can be verified by geophysics? What are the unknowns, and is there a method that can measure them? Very important when we come onto the geophysics is to know exactly what you're trying to measure. Is the proposed method likely to have sufficient parameter contrast? So there's different kinds of physical parameters that you can measure. So the one you choose, it has direct bearing on what answers you're going to get. And if you choose a different method, you'll get different answers. So you need to know what your survey goals are. Another key parameter is the limiting depth of the proposed method. And the final question here is, can a geophysical method improve the design or reduce the failure rate of the proposed borehole at either the preferred location or a nearby alternative? And then based on that, you select the borehole target and a suitable geophysical method. And I'm not really going to speak about level surveys, but I thought I'd just remind everybody what it's like to do a level survey or even a geophysical survey in Africa. So we'll just run this video and see what happens. So there you have it. All surveys attract an entourage, and that is a fairly common sight for if you're carrying out a survey. That instrument has a huge attraction, and all the local kids will be wanting to know how it works and what's going on. So onto the geophysical survey itself and the planning process. As I've kind of mentioned already, there's a triumvirate of decision points that are key to the geophysical survey planning process. And essentially, there are three fundamental limitations that help to determine what is the best way to what is the best method to select. And you have to look at those three and see whether they're going to achieve the investigation goals and see whether those are going to be met. One of the possible answers is that geophysics is inappropriate and it's better just to proceed directly on to drilling, because it may be that you have a circumstance where none of the geophysical methods work. So what are those three things to consider? The first one is cost, and that could be either measured per kilometer or the cost per day. For our purposes, the cost per day is the most important one, but because we're typically looking at a specific site rather than trying to get a map coverage. And we'll cover that right at the end. Then the next one is the penetration depth. Every method has a different penetration depth, and some are unable to get to the depths that boreholes typically extend down to. So, but still cover wells and shallow boreholes. So, penetration depth is a key factor. If your goal is to put in dug wells, then most methods will work. If your goal is to put in a deep borehole, then a fair number won't. And then the parameter contrast. So are you trying to measure the rock density, or are you trying to measure the resistivity or conductivity, electrical conductivity of the rock? Because depending on what parameter you're choosing, you can then get different answers. And each of those has a specific benefit. So you need to know what your goal is, and that then once you know the goal, then you can look at the various geophysical methods, see whether there's a parameter contrast that you can measure that's likely to be present in your study area, and then you'll apply that method. it's always important to remember the alternative form of Newton's definition of madness, which is that undertaking a survey and expecting limitations to be exceeded is, by definition, madness. It's very easy to think, oh well, the penetration depth is 30 meters, but I've got my borehole will go to 60, so it might give me some indication, but more than 30 up to the 60. Sadly, that won't be the case. The penetration depth will be what it is, and it could even be less if you have less than optimum conditions. So just a brief overview on cost, so you get a feel for how expensive these surveys are. The ballpark cost for a new geophysical instrument is around 50,000. Now, some are quite a lot less and some are quite a lot more, but that's a good indication. Used instruments are at least half price. It depends on how good their condition is. And ballpark instrument hire costs in the UK will typically be about £2,000 to £3,000 per week. And a UK operator will typically cost somewhere between £500 to £1,000 per week, and a typical international hire from UK is 2 to 3 weeks. So with a minimum of 3 days out to reach your survey location, 7 to 14 days for the survey, and a minimum of 3 days to return, then you end up with a 2 to 3 week cycle. So obviously you then end up with a fairly large number for a hire from the UK. Now, that basically, as we'll look at in a bit, will exceed the value of a borehole. And you're probably just better off just banging in a borehole and getting and seeing what you get. Now, the alternative to this is to use local hire, which will be lower cost, but not as lower cost as you might think. So often you're in the range of half price rather than 10% or something like that. But the main issue locally is operator quality, which is highly variable. Some surveys are not worth the product. In other words, they'll tell you misleading information if they tell you information at all. But in some cases, the suppliers will be of good quality, and if you know who they are, then you can go to them and get a reliable survey, and that's definitely the better way if you've got a good quality supplier. Unfortunately, the process of finding out who's good and who isn't takes time, and of course there are a few false dawns in the process. And then the methods themselves. So this next section is just to go through those various geophysical methods. The first one to consider is the magnetic method, because it's a very simple method. You can see here on the left is an operator. He's carrying his magnetometer on a staff. That staff will give him a constant height. So when he reaches the point to measure, he just plants it on the ground and then gets constant height. I mean, you can also get backpacks with this method, so he can literally continuously survey as he walks. And this instrument that you see here also has the opportunity to you can use an electromagnetic method with it, the VLF method. So you can actually survey with that box, getting two parameters at the same time, the magnetics and the electromagnetics. What I'm showing you here is just the magnetic version. And so a bit of detail about how the magnetic method works. So the ground anomaly, that is the magnetism of the ground, is superimposed on the Earth's magnetic field. And the Earth field fluctuates during the day and the night. So in order to get a corrected ambient field, a base station is placed at a location with low magnetic gradient, and the fluctuations in the ambient Earth field are measured, and then that's subtracted from the local magnetic measurements that you have at each location on the survey, and that will then give you the Earth field. Now, the key thing here is that magnetic field reduces logarithmically with distance. So this means that if you have an airborne survey, then you either have to have a much more sensitive magnetometer to measure what you're measuring on the ground, or you're going to have less penetration depth. And now, so that means that you have the advantages of airborne are quite limited, on top of which they're extremely expensive. So effectively, magnetic method for our purposes is limited to ground surveys. And that means depends on the instrument, but the instruments that measure total field, and this one here is a proton magnetometer. It has a depth resolution of about 50 to 100 meters, depending on how strong the magnetic field is from the geological feature you're measuring. Another advantage of proton magnetometers is their relatively low cost compared to other geophysical methods. And a used instrument can cost as little as £5,000. It's a rapid method, so you can measure 1 to 2 kilometers squared per day at a 50-meter line spacing. Essentially, it's a walking speed survey. The misfortunate element is that although it can measure down to borehole depths, the method has limited hydrogeological applications. However, it is a good method to identify dikes and intrusions because they have strong magnetic characteristics. But in some locations, and this is typical of East Africa and the rift systems of East Africa, the dikes are poorly fractured because they're young and they act as a dam wall to the groundwater flow. So they indicate locations to avoid for new boreholes. Whereas if you're in a cratonic terrain and basically very old rock, which you get in Tanzania, Botswana, Zimbabwe, and South Africa, and a number of areas in a small area in Kenya and a larger area in Uganda, then the dikes that are identified there are old and therefore well fractured and are actually excellent borehole targets. So essentially you drill your well into the dike, and the dike then acts like an adit and provides water to the borehole. And the magnetic method is a very good way of identifying where those dikes are below the soil level. Okay, so the second method is the gravity method. It's in physical terms, it's very similar to magnetics. It's a gravity field, and it's measured by this little small box here, which has to be leveled. And every time you move it, you have to isolate the spring. In other words, lock it in place, then move it, then unlock it, and level it, and then take the measurement. So it's the measurement cycle's quite slow. The gravity anomaly varies due to the topography and variation in density of local rocks. So if you've got a hill nearby, this instrument will measure it. If you're sitting in a valley, this instrument will measure it. And it also measures the variation in density of local rocks, which can be quite small. You're talking of about 0.1 to 0.2 grams per centimeter cubed. And it can measure the difference in density of the soil layer compared to the bedrock layer in a river valley. So it's a very sensitive instrument. Now, the gravity field is more complex than the magnetic field, but it also fluctuates day and night, but it's also affected by the moon in particular and other components. So there's a tide fluctuation in gravity that the Earth experiences, and this instrument measures that very well. Secondly, it's actually quite the absolute meters are not very portable, so it's only measuring the relative gravity. So again, it's necessary to have a base station, and the base station, and then your survey is measured relative to the base station. You're not measuring absolute gravity, you're measuring the difference relative to that point. And in order to get that measurement, you have to measure out the fluctuations of the gravity field, which is measured by the base station. You have to impose a topography on it and then calculate what effect that topography would. In other words, you're correcting it to so that it imagines that it's got a completely billiard table flat surface. And then after you've corrected those two elements, then what's left is the residual component, is the gravity field from the rocks at the position of measurement. Used gravimeters cost around about £20,000, and it's feasible to measure about 100 positions per day. So at a 50-meter measurement spacing, a ground survey can cover 3 to 5 kilometers per day, depending on how long it is and how long the battery lasts. As I mentioned earlier, the method determines the unconsolidated soil depth in river valleys in basement rocks, which usually have a high groundwater perspectivity, and that's the main value of this instrument. Is you can when you look at a river valley and it's got sands and gravels in it, those sands and gravels may only be 5 meters deep, in which case the best you're going to do is going to have some kind of well in that system, which is 2 or 3 meters deep. But in other locations, the river valley will be very deep, and you may have as much as 50 to 100 meters of sands and gravels, and that's highly prospective. A borehole in those conditions will be highly productive, and the gravity method is one of the ways to determine how thick that cover is. The main problem with the gravity method is that there are multiple solutions to any measurement. So you could come up with one solution that's 10 meters deep, one solution that's 30 meters deep, and one solution that's 50 meters deep. So in the microgravity method, what you do is you run a cross section from where the rock at the side of the valley is exposed, then go right across the valley and come out at the other side to the rock that's exposed on the far side. And where the rock comes out, you're basically in the bedrock, so there's no, you know what that measurement is of that bedrock, so you get that's now measured. And then as you go across the sediment fill, you get a lower gravity, relative gravity, and that is caused because of the porosity of the soil layer. And from that, you can then tie down the estimate to pretty close to value. Ideally, you would have a borehole which proves the thickness, but that would then defeat the purpose of the survey. The other limitation is it doesn't indicate water quality or differentiate clays from sands and gravels, which can be measured with other methods. And we'll look at this example in the typical examples at the end. So speaking of the vertical electrical sanding and resistivity method, we'll go through this now. The VES method, which stands for vertical electrical sounding, is the most widely used in groundwater geophysical surveys in Africa, and you can see an instrument being used on the left. Essentially, it comprises of 2 outer electrodes where current is put into the ground, and then it passes through the ground to the other one on the outside. And then the 2 electrodes near the middle then measure the potential difference. And the instrument then calculates the resistivity from the combination of the measured current and the measured potential difference. No, it's fortunate that the electrical methods are differentiate quite a bit. So they're able to differentiate sands and gravels from fractured rock and unfractured rock. And the reason for that is that it's not so much the fractures that you're measuring, but you're measuring the water that sits inside the cavities, or porosity as we call this in hydrogeology. So the higher the percentage of porosity, the higher the percentage of water in the rock, and the more conductive it is, and that then shows up in the resistivity. Some clays also show up well because they are more conductive than the other granular rocks, and they have because the clays have low permeability, they act as a pipe walls to sands and gravel layers and to rock layers as a whole. So it's good to know where those clays are. It can tell you where you've got low prospectivity, and it will also tell you whether you've got confining layer. And the other thing that shows up very well in resistivity surveys is the water quality, because conductivity increases sharply with salinity. So you can distinguish fresh water from brackish water and brackish water from saline water and brine. Now, the method is insensitive to vertical fractures, and there are other methods that achieve that, and fault locations, and yeah, as I said, you can detect those with other methods. And the method works like this. So if you take 3 layers with 3 different resistivities, this is the ground layer here, and you've got your 2 central pins in here. The average depth of the current path between 2 electrodes increases with electrodes separation. So if I show you 2 electrodes here, that will be the path of the current between them, and the potential difference is measured in the center here. The close separation will then give the surface layer, but if you increase the electrode separation, you're going to get progressively deeper descent of the current, and as a result you can then build up a model by subtracting each layer from the ones so subtracting the layers above from the one that you're trying to measure, so you effectively get a layer by layer model. And if you use curve matching, which is how this was done historically, then you can get up to 3 resistivity layers using this method, and often that's all you need. But with modern computer slice modeling, you can the resolution is improved substantially, and you can get quite a few more layers. Although, interestingly, when you use this method, you often end up with only 3 layers anyway. It seems to be one of the rules of life. And the reason for that is that the top layer will probably be the layer above the water table. The next layer will be the water table down to the rock head, and the bottom one will be the rock head, or the unweathered zone. So the reason why that's often the case is that the weathered zone often is also quite porous, and so it's often more hydraulically conductive. So often the water level is also a function of those layers as well. So that's the resistivity method. Now, the VES method essentially just measures layers, and it's a bulk value for each layer. But it is feasible to measure the zones within each of those layers using another method, which is well, before we get on to that, we'll look at this next slide here, which is, as I said, the VES method measures the bulk resistivity, and that limitation is overcome with the ERT method, which we'll look at in the next few slides. And the ERT stands for electrical resistivity tomography. Now, the VES method, which is just the layers, because it's a bulk method, it's insensitive to the rock fractures that are a dominant flow mechanism in the majority of boreholes in Africa. However, the ERT method partially determines those rock fractures, because it looks at it basically provides a much greater resolution of the resistivity within each layer. Used instruments, resistivity instruments, cost about £10,000, and the survey line lengths of 120 meters on each side of the instrument are usual, which will give you a depth of about 60 meters, and you can add an extension cable on either side to give you another 120 meters, to give you 240 meters. That would then give you a depth of around about 100 meters. So basically, this method can extend down to the depths you need for boreholes. In theory, you could extend those lines up to a kilometer on either side, but it becomes extremely unwieldy, because you've got to walk out for a kilometer unrolling all of your cables, And then you've then progressively got to connect up each electrode, and then as each electrode is each measurement takes place, you've got to expand those electrodes out further and further along that line, which takes a very long time to carry out a survey. And there are other methods that will achieve that more efficiently, on electromagnetic methods that we'll talk about a little bit further down. Nonetheless, the VES method gives a depth range of about 60 meters on one reel and about 100 meters on two reels. And as I said, depths to 400 meters are feasible, but are impractical. And what it does is it gives you this curve. The AB over 2 is the AB is the distance between the two outer electrodes, and so AB, because it's symmetrical, AB over 2 is the half width, half length, and then the depth as an indication is around about 2/5 of AB over 2 that you're actually encountering, and that's the layer that you're actually measuring. So if I've measured, as you can see here, up to around about 150 meters, then the depth I'm going to get down to is of the order of 60 or 70 meters. And then I can then use a computer model, and that's what we can see on the right. For a reason that is always obscure to me, these models always show depth on the x-axis because that's an x-axis variable, and the y-axis is the resistivity. But to my mind, this should always be rotated 90 degrees, and you should be showing depth from 1 to 1,000 on the left, and then have a y-axis, effectively the x-axis across the top. Anyway, nonetheless, you'll notice that in this particular example, there is a layer down to 25 meters, which has a relatively low resistivity of 100. And then as you come up from here, there's essentially a couple of transitional layers, and then you eventually reach about 10,000, and that's at a depth of about 80 meters. And what you're seeing, and also this top layer is got a fairly high resistivity. Now, when you have no water in soils, obviously the resistivity is much higher. So what that's really telling you is that you've got a water level that's around about 3 meters, and then you've got a weathered layer with no clay, because clay would have a much lower resistivity, and that's takes you down to 25 meters. And then you've got a transition from this soil horizon or weathered rock horizon up to the more consolidated rock around about 80 meters. So this next zone between 25 meters and 80 meters is fractured or variable weathered component. So what it's telling us is that a borehole in this location should be quite good, because we're going to be able to get we would expect to get fairly productive water supply from 25 meters to 80 meters, which is the main productive zone of 100-meter well. So that's a good result. Now, in electrical resistivity tomography, instead of just having 4 pins, electrode pins, you have a lot of them. And you in this particular example, you see here is a modern advance which shows how to get a 3D image instead of just a 2D image cross section. But you can still use tomography just in a section. So where you would basically what the method does is it enhances the VES method by essentially adding a switch to each of the electrodes, and then what you do is you pin in all the electrodes all at once, and then attach the cable through the switches, and push the button on the machine. The machine then does the various combinations one by one. And what it means is it can take, near the surface, it can take the resistivity between each of these electrodes, and it'll continue all the way down the line. And then when it wants to go to the next layer, it'll then do every other one, and then the third layer, every third one, and so on until it gets to the bottom. And so for a section, you lay them out in a line, and if you want a 3D sounding, you lay it out as shown in the picture. The instrument then automatically selects and measures each electrode group, and the tomography software calculates the resistivity for each zone and depth layer. And in this example above, you can essentially get a plan view, but you can also get a section view on through this particular example here, which is of a contaminant plume. It's a very sophisticated method, and it's generally not available in Africa, which is unfortunate because it's now been used in Europe for more than 30 years. So it's now quite a mature methodology, and it's something that would significantly improve the borehole evaluations if it was available. It genuinely isn't. Normally, the method you'll find from local suppliers is VES, not ERT, partly because ERT is more expensive. So that concludes the resistivity method, but it's very similar to the electromagnetic method. And the reason for this is that the electromagnetic method measures conductivity, which of course is the inverse of resistivity, and so you get very similar results. So EM is the method we're going to look at now. Now, there are a number of different EM methods, and they measure to different depths, and have benefits and disbenefits. So the first kind of electromagnetic method are the frequency domain electromagnetic methods, or FEM surveys. And these methods can measure resistivity down to 40 to 60 meters depth. When I was at university, VLF was basically had a limiting depth of about 40 to 60 meters, but at least one of the manufacturers has improved this methodology quite recently, and it can now reach 100 plus meters, which makes it very useful for borehole. Unfortunately, it uses the signal from marine radio broadcasts, which have the right frequency, which means that it isn't universally available, and some parts of Africa it's not feasible to use. And the third kind of electromagnetic method is the TEM method, which is the time domain electromagnetic method. And these are slower, but they offer depths of 100 to 400 meters, so are very useful. But they're also quite expensive. So when you're doing a EM or resistivity survey, it sometimes makes sense to do a combination of FEM and resistivity, the VES method that I just showed you. So because the EM is so fast, you can cover the surface very quickly. It's basically a walking speed survey. And then if you find something of interest, although you've only got a penetration depth of 40 to 60 meters, you can then follow up an area of interest with a VES or a ERT method to confirm that site's appropriate for a borehole. A little bit more detail on the VLF method. Now, this is frequency domain. So basically what it's doing is it's measuring the change in phase between the signal and the received field, which contains the induced EM field. And then it separates out the two and determines the conductivity of the ground based on the change in the phase. As you can see here with this backpack method, it's combined with a magnetic survey. So the VLF instrument is this one here on the gentleman's back, and then you've got two magnetometers, so you can get the magnetic gradient, and then this instrument at the top is a GPS, which will then give you a position for each measurement. It basically covers about 25 kilometers per day at walking speed, and the manufacturer, which is GEM Systems, claim 100 meters plus depth for the VLF method. due to improved receiver resolution and computer inversion software. But as I said in the preamble, VLF transmitters are not available everywhere. As you can see on this map, there aren't any in Africa. The good news is that you can still measure some distance away from the transmitters, but essentially it means that it's only feasible to carry out measurements in the northern half of Africa and in the northern half of South America. But beyond that, in the two southern halves, you're not going to be able to use the VLF method, which limits its use for the kind of surveys we want to do at CED. So alternative to the VLF is to use the EM34, which is produced by Geonyx, which is these two rather funky orange discs. No, they're not Frisbees, they are sensitive instruments. The limitation here is that it can only measure ground conductivity to 60 meters. And it does require two operators to keep the two discs at the correct separation. So at 60 meters, you're going to need a 30-meter separation between the two of them. And so the two operators just basically walk in sync to keep the right distance apart. And it's still feasible to get a good coverage. And when you get an area which looks promising for a borehole, then you can finish off that survey with the ERT or VES method. And because the EM34 uses a transmitter, so one of these coils is a transmitter and one of them is a receiver, essentially it can be used anywhere, which overcomes the VLF limitation. Okay, so that's enough on that item. The final option is the TEM, or time domain electromagnetic method. And here is the two instruments produced by Geonyx with a transmitter box and a receiver box. In one, the TM47 transmitter and the ProTem47 receiver. And the way this method works is you connect the transmitter to a circular coil system that you lay on the ground, and that typically will have a 100 by 100 meter radius. And then you take measurements with the receiver inside that coil. But the time it takes to lay out that 100 meter by 100 meter ground induction loop takes a fair amount of time. And so the method is quite a lot slower than the previous electromagnetic methods that I showed you. But the advantage is that by selecting the right time interval, you can then measure the ground conductivity up to 400 meters depth. And essentially it's the depth, it can go much higher than that. It just depends on how powerful your transmitter is. Essentially the survey rate is about 5 to 10 measurements per day. So if you have a spacing of 100 meters, then you can cover around about 1 kilometer a day. So obviously this method is optimal for deeper boreholes or locations where the groundwater levels are quite deep, and therefore you need to know what's going on from the water level downwards. Disadvantage being the cost. Okay, so now I'm going to just close off with a couple of methods that generally we don't use in groundwater because they're either too expensive or they're too shallow. So first of all, the seismic method, which most of you will be familiar with. Obviously, it measures the seismic wave velocity, and the velocity of the seismic waves is a function of rock density. It provides a definitive layer depth, and top of bedrock identifies faults and discontinuities, so it's a very powerful method. However, depth is limited by the power of the seismic source, and this is where the real issue is for our purposes. If you use a sledgehammer and plate, which is obviously low cost, that's exactly what we would want to use, we can only reach 20 meters. Alternatively, we can use a trailer with a weight drop on it, and that will get us down to 1 kilometer if you're in ideal conditions, but certainly well past the depth that you want for a borehole. The problem is that you can't put a trailer and a heavy piece of really heavy weight in your baggage on the plane, so it's not something that you can easily transport to most of the locations we go to, and in general, it's not available locally. The third option is a fiber-sized truck. Obviously very expensive, has to be imported. It's way past our cost bracket. And the fourth one involves an awful lot of licensing, because to use explosives requires licenses, and it also has its own expenses because you've got to drill the explosives to the depth where they then basically blow the top of the hole out and instead give you a nice seismic trace. So long story short, the seismic method isn't that useful for groundwater studies because there's no feasible wave source that's in the right price bracket. The instrument itself is also quite expensive, so as a whole, that's not something that we use. Nonetheless, let's have a look and see how it works. So if you have a source here, you then lay out a series of geophones, and the first of those geophones will actually be a trigger which will tell the instrument to start the measurements from the geophone array. Essentially, what you're doing is measuring the travel time along the inferred wave path, and that gives you a velocity. And you've got two layers here, velocity 1 and a more dense layer with velocity 2. And we're going to measure the depth. The velocity is a function of the elastic modulus of the rock and divided by the density, but the latter is the dominant parameter. And there are three wave paths from the source: the direct path, the reflection, and the refraction. So let's look at each of those. So first of all, the direct path, that obviously is along the surface to each of the geophones. Then you've got the reflection path, which is follows the two blue arrows. Because it's a reflection, they're symmetrical about the point of reflection. And so if I measure the reflection at this geophone here, then I know that the point where I reflected is half the distance between me and the source. So that's at this position here. And from that, and from the travel time, we can then calculate the depth because you've got a triangle which allows you to do that. Refraction's more complicated. In the refraction case, there is a critical refraction angle at which the refracted wave will then travel along the top of the lower layer. Now, because the lower layer has a higher density and the velocity will be higher, so what then happens is that this refracted wave will actually arrive at this point before the reflected one. And so you'll then get two traces, the first one being the refracted, and then the second one will be the reflection. So again, because you've got the two traces there, you can tell the first one's refracted and then you can calculate it. And the reason for that is that the refracted angle occurs at a particular angle based on the ratio of the velocity of layer 1 and layer 2. And not only that, as you go to your outer geophones, you'll get an arrival time for each of those, which will also have reflective waves as well. But the refractive one, if I just continue the process, you'll get a whole sequence of arrival times as you go out along the geophone. And the same would apply to the reflection, but I just didn't show it because it became too complicated and too busy on the diagram. And the final thing is that there's actually more than one kind of seismic wave. So you get pressure waves, shear waves, which are known as S waves. First ones are P waves, and surface waves. And the good news is that the velocity of P waves relative to shear waves is almost double. So as a result, again, you can distinguish between the reflection and the refraction of the P wave, and then similarly the reflection and the refraction of the shear wave. And all this means that there's a lot of processing required to identify the arrival time of each, and that's one of the reasons why the equipment itself, the box, is quite expensive. And then you've got fairly expensive software to do that. It's a fairly involved method. So all in all, we don't use this method, but it's nice to know, and it does give us a very reliable depth between different density layers. So it's a great one for identifying the top of bedrock. Similarly, the radar method we don't typically use. This one is the noggin. It has it basically can measure down to 20 meters. The radar is fantastic because it produces high resolution surveys for the near surface, so it's ideal for engineering problems like pipes, but less useful for boreholes. Again, the radar method is using a reflected echo from layers and ground objects. It gives accurate cross sections and near surface layers and discontinuities. But as I said, the depth limit is the main issue. And so it's of limited usefulness. So how does that look? Well, as you can see on the right here, you get these characteristic U-shaped reflections that occur both at the top and the bottom of the pipe. So there's a pipe sitting between these two, and then you get multiples below that. And then where you've got these constant lines, then those are typically layers, but sometimes you can see utilities as you're passing through. Now the main issue is that the radar, which essentially is close to microwave frequency and wavelength, and gets strongly absorbed by the background, as you can see in these two pictures here. So the instrument uses stacking, just like the seismic method, in order to improve the signal to noise ratio, but even that can't get you beyond around about 20 meters. Good news is that soil and rock type doesn't significantly modulate the beam, so it basically becomes, the interpretation comes fairly straightforward. And you can, a small little instrument like the noggin here, it's pretty basic, and it produces very good results for the engineering surface. In other words, 0 to 20 meters, but it's of limited use in groundwater. So that concludes the discussion on the methods. So I'm just going to go through some practical examples. This one here is the ERT method, and here there were a couple of lines that were done. This is the method where you peg the instrument into the ground, and you get a series of pins. You connect them all up, and then the instrument then measures between each of the electrodes to get the resistivity of the ground. And there were two lines that were done, one here, and you cross the main road, and there's another line here. And the other key bit of information is that this here is the beach, salt water is here. So essentially our concern here is the water in this area going to be salty? Is it going to be suitable for boreholes or not? And the first section is this one here, which runs, line A, it runs from the beach, which is on the south end. So unfortunately, I could have turned this around, but then all the numbers would have been back to front. So unfortunately, it's a bit of a brain twister, this one. But essentially, this area here is where the salt water of the sea is at close to ground level. And then because of an effect called the groundwater interface, fresh water floats on top of the salt water, you get a wedge that spreads with depth. And so what you're measuring here is the salt water interface. And then you've got fresh water in the sands and gravels in this section up here. Now we know it's sands and gravels because the groundwater level at the sea level here is 0. So in this area, the groundwater level is also about 0. So the fact this brown and red area extends down to 20 meters tells us that there's 20 meters of fresh water in here. And then you get a transition into salt water. And the sands and gravels have a resistivity of the order of 200 upwards. So that's why you're seeing basically the yellows to reds are the sands and gravels. Everything else is the transition. But then at the other end of the line, there's a transition up here that looks like salt water's coming close to the surface, but it could also be clay. So if we look at this section here, you can see that is continued in this section here. And this area is the side of a gravel pit where all the gravels have been extracted. And so it's either because this area is filled with brackish water, salt water, or it's because the clays are preventing the area being filled with fresh water, because the rain can't get to those layers underneath. And you can see that in this section here. These greens, the top green is the dry location above the groundwater level, and this green here below that, that's the clay. And then once you get into the blues, that's probably salt water. So the method's very powerful at distinguishing exactly what's going on. If I was going to have a water supply here, I would have a shallow well in this section, in the sands and gravels, and that would produce a fairly good water supply. But in this section, definitely one to avoid. And the geophysics tells me where to go to do that. Okay. So an example from Ethiopia. This time I'm going to use microgravity. This here is a wadi with a thick sands and gravels base in it, and we want to know, can we get water out of the wadi sands and gravels? On either side, we've got Precambrian basement rocks with poor fractures and poor prospectivity, and that's also the same here. So one of the methods to do that is with a gravimeter. Here is a gravimeter being used at a base station, and then we just go across the wadi, taking measurements. Once we've done that, we'll then get a profile of the relative gravity along the chainage of that particular section from one side to the other side of the wadi. And then we can use a model, because we've got bedrock at the side here and bedrock at the side here, we know what that bedrock relative gravity should be. And then the model then calculates the differential reduction in density of the fill of the sands and gravel clast. Now, most of these sands and gravel clasts are made from Precambrian rock, so it's the same rock, but it's the porosity that changes the density. So that's basically telling us you have a 20% porosity, which is pretty much bang on what you'd expect for a sands and gravels. And then you can, if you have a number of sections on them, you can then produce a graph to show where the bottom of the wadi is and what shape it has. But ultimately, from a hydrogeologist point of view, I want to know how deep that is, and in this, and can I get a borehole in it? So the answer to this is yes, I could get 50 meters. In sands and gravels, that's probably more than enough. Unfortunately, it turned out that the groundwater level was very close to the bottom of this unit, because effectively the sands and gravels were acting as a French drain and draining the bedrock and transferring it down the wadi. So although it looked dry here, there's quite a lot of flow, but it's in that bottom 2 to 3 meters. Nonetheless, the gravity method, as you can see, it's a very useful method for determining the cover rocks and the depth of the cover rocks in a river valley. Then the TEM method, again, if you continue down, this is actually a little bit further down from that same wadi. We're on the sands and gravels of the fan, the sand and gravel fan. As you come down the fan, it transitions. This is the fan here. That's where it comes out of the wadi. You then get a transition into brackish water, and then if I go one step further, that brackish water transitions into brine because of the salt evaporation. So question then is, are we able to access the water in this alluvial fan? And is that water fresh or is it salty? So we would want to use ERT, the resistivity method, but the thing about electrical pins is that sands and gravels have a very high resistivity, and it's often very difficult to get a good electrical contact using the resistivity method. So this is where the TEM method comes into its own, because it doesn't need a contact and you can just walk over the sands and gravels. So once you've mobilized it, you then are able to make a reasonable measurement. And what the TEM method shows, you can see each of these locations is a measurement point. If you use the contouring software between each of the TM methods. Each TM sounding will give you the connectivity with depth, and then you can then essentially produce that in a section. And what this here is the alluvial fan. You can see the slope of the fan heading down towards this point. This is the point where you're in the brines, and this here is the brackish area. As you can see, that's the brine, that's this end. Here's the brackish, that's about there. This is the fan, this is this area here. And what that's telling us is that there's about 150 to 200 meters of fresh, non-salty sands and gravels. And the transition around about this level here is the transition, that's the water level, basically the water table. So it's basically saying there's about 100 meters of fresh water in those sands and gravels. So that's a good target. And then when you transition into this area, which is the Precambrian bedrock, you can see you get very high resistivity. So that's because there's very little porosity in the bedrock. It will still produce water because it's old and it's quite well fractured, but the really productive area is this area here, and the electrical method shows that up really nicely. Now we can look at this section at the top here, in this second section here, which is in a slightly different waddy. Essentially that section runs up this waddy and in this direction, and it passes through off the alluvial fan into red sandstones, then into limestone, then into a more dense limestone, and eventually into the Precambrian bedrock. And again, you can see this is the end of the sands and gravels here. These are the red sandstones. This here is the limestone. This is the very dense limestone, which is probably Cambrian limestone, so it's much older with very little porosity. So it shows up in a different color from the Jurassic limestones, and then eventually you pass into the Precambrian, which you can see here. It's here at depth, and at this point it's at the ground surface. So the electrical methods are very good at differentiating the geology that you get, and you can get very good groundwater information. Because the time's marching on, I'm just going to just say that this is a table which covers what I've said so far. Well, you can look at that at your leisure when we hand it out. So once you've got that geophysical information, you can then define your borehole construction plan, and the geophysics will hopefully help identify the optimum location, target, and borehole depth. But you need to review whether the unknown parameters have been defined. Is the target aquifer defined? Sands, gravels, limestone, sandstone. Have you identified one of those with the geophysics? What's the likely water depth? What's the likely aquifer permeability and transmittivity? Have you identified rock fracture zones? And have they been identified and optimized? Has the aquifer thickness been identified? And what is the likely water quality? Is there salt water at depth? And based on all that information, you can then develop a borehole outline design, and from that go on to producing a more detailed design. So the conclusions. What low-cost geophysical survey methods can do? Low-cost geophysical methods measure the following. Low permeability boundary layers, so that's clays, and that can be done with the seismic method, TEM resistivity, and the FEM method. You can measure faults and barrier boundaries, such as dikes, with a magnetic, seismic, and resistivity and the FEM method. The thickness of river valleys, sands and gravels, and/or alluvium. I didn't go into this in much detail, but you can also measure the vertical fractures using the two little circles of that method can often give us good vertical fractures, because you can use the circles in the vertical sense and you can use them in the horizontal sense, and the difference will then be sensitive to vertical fractures and insensitive, and by comparing and contrasting you can get an idea whether you've got vertical fractures or not. And of course, you can use geophysical methods to determine the water quality. However, it's always important to remember what you can't do. Geophysics doesn't measure permeability or transmissivity, and these can only be measured by well pumping tests. And the best way to get those is to canvass nearby borehole users and find out how good their boreholes are and what their issues are. Groundwater flow paths, that's best determined at test study stage from the methods I spoke about in my previous talk. Similarly, groundwater flow rate, that's something that can only calculate once you know water levels and transmissivity. And groundwater level and gradient, again, is something you're going to have to wait until you get your borehole in to find out precisely what your level is. There's always going to be a certain amount of uncertainty in even after the geophysics about that. And as I mentioned in my previous talk, engineers measure in millimeters, but hydrogeologists and geologists measure in meters, because that's the difference in uncertainty. Our tolerances are much wider, but equally the uncertainty is greater. Now, here's the issue that we really need to cover on this topic more than anything else. There is an elephant in the room here that I haven't spoken about, which is the cost. So here's an example of how the costs work out. A single 6-inch borehole drilled to 30 meters costs around about £5,000 to £10,000. Now, UK hire was typically £5,000 to £10,000 as well. So if I'm going to use a higher instrument from the UK, and let's say there's a 25% borehole failure rate, then I'm going to need to drill 4 boreholes before that survey mobilization cost is recaptured. And most of the time, we're only interested in drilling 1 borehole. So is there any point in doing the survey? It'd be better off just drilling 2 boreholes, 1 failed, 1 works, and Bob's your uncle. Good question. Alternatively, we could use local hire, which is say 50% cheaper, and that essentially will then still have the same problem. It's about the same cost as having of drilling 2 boreholes, 1 fail, one fine. And then, of course, with the local hire, you're not sure how reliable the supply is going to be. There's a fairly high incidence of very poor results. So you have to be very careful with local suppliers. Having said that, I've worked with Ethiopian suppliers who are first class and would be more than hold their own in the UK market. So it just depends. Now, another possibility is to use used instrument purchases and then use those on multiple surveys so that their cost per mobilization is much smaller. And that option works quite well, because now you've got reliability and now you've got a relatively low cost survey. Now, it may be that the cost benefit is limited, and therefore an experienced hydrogeologist will say, nope, based on my experience, I'll decline a geophysical survey because I've got a reasonably good idea this is going to work, and the cost of the geophysics isn't going to significantly advance my understanding, so I'm just going to drill. But in counterpoint, a geophysical survey provides greater cost reliability and cost control. So it's a favorable approach for boards and donors, because now they know what the cost is. They're not going to have any nasty surprises of, oh, I need another borehole. And if saltwater or brackish water is present, a geophysical survey is essential. Thus, on balance, geophysical surveys should be undertaken, but only if the selected geophysical method has a high probability of success. And a used equipment policy should be adopted, especially where local suppliers are not available. But if there are local suppliers, then that's probably the best option. It just depends on price. So there we are. That's the end of the presentation. Thank you for listening.
Well, Malcolm, thank you very much for all of that. Now I'm just going to try and unmute everybody. And I'm going to ask everybody to unmute. So you've got to unmute yourselves. and you have been pinned, and I'm going to unpin you, which means it's been focused on you. Remove pin. So there we are. And if you could you stop sharing your well, unless we might want to go back to something. So
I'll come back if necessary.
okay. So I think that certainly has convinced me that not something I'm going to go out and have a go at. This is something that is a mixture of engineering and science and sort of the dark arts. There's an art to it. Would that be right, Malcolm?
Yes, I mean, I think the goal of my presentation was to give an overview so you know what can be done, and
Yes.
therefore that helps with the planning. I mean, ultimately, you any of the surveys you would probably want to give it to somebody who knows what they're doing. And so as I explained at the end, it's very important that you don't just select anybody, because certainly if you're using a local supplier, there are significant risks, and I would say even substantial risks. However, some of the local suppliers are excellent, and if they've got good reputations and and you know them well and they've proved themselves, then that's definitely the best route. But there are other ways of doing it. Um, the, the issue with having our own equipment is it's a very big outlay, and there's a whole load of issues around that. So, but from a purely flat, here's a good way of doing it, that would be the best way to do it. Whether that's actually feasible within the our organisation's another matter, but that would be one way of doing it, and it certainly in locations where there are challenges to getting things done right, and Sierra Leone is one of those places, then that would be a place where you would definitely want to have your own instrument and do it yourself.
Mhm.
So so yeah, the goals were to show what can be done, and the once you get your head around a particular method, it's actually very straightforward, and you only need a minimal amount of training to know how to do that. The interpretation is probably the biggest challenge, and there are, as with all methods and all engineering, there's a learning curve involved. It's not it's not for somebody who has an engineering mind, I don't think that the instrument part of it you'll pick up very quickly. The bit that's more opaque is quite what that means in terms of groundwater, and even geophysicists often produce excellent results, but they don't fully understand what that means for a groundwater client. And so one of the areas that I've been able to contribute is to be able to interpret what the geophysicists are saying and tell my groundwater colleagues and managers what that actually means, because the reports often don't do that, and miss quite a few opportunities.
Mhm.
I'm not sure what that answers the question, but I think it.
So is your suggestion that CED, well, I suppose a suggestion is that CED could buy secondhand kit, hold it in stores, and use it as and when we want to go.
It's certainly I'm certainly mooting that. Yeah, I think it needs further discussion, and that may or may not be appropriate, but it's certainly something that should be discussed, even if it's not something that's adopted.
Yes, and the payback in terms of how many boreholes we would have to do to make that a worthwhile route to go down, was that in the order of 10?
That is, yes, exactly. That's kind of where the mathematics starts being beneficial. Keep in mind that it also there's also a fair amount of servicing costs because of wear and tear on the instrument. And if you've got a second-hand instrument, that wear and tear cost will be higher, just like it is with your car. So there are pros and cons. I'm not 100% convinced it's the right solution. I haven't spent an awful lot of time exploring who's available in uh, but I think in East Africa, probably local suppliers will be the preferred route. And if we're staying in East Africa, then that may well be the right answer. If we're not, or we're in other locations, then the alternative, having our own equipment, may be the solution. but as you probably gathered, there's also another issue, which is that you probably would need more than one kind of instrument, and so again the prices start mounting. So I'm personally not 100% convinced the used equipment route is the right route. Um, the key caveat to take on board is the fact that geophysics surveys are expensive relative to the cost of boreholes, and getting the right balance is a tricky balancing act, and it needs input from somebody like Barbara and Ian to say what is the corporate and board level perspective on it. How important is price certainty? Because that's where the geophysics comes in. Because you can argue then, well, it's worth having the geophysics even though it adds a few thousand onto the price, just because I'm going to get price certainty. That kind of feedback is part of the decision matrix, and the other part is just the engineering part of what's the cheapest way to get to the answer. And often that can be drill and go. But Ian and I are currently working on a project in Tanzania where a local supplier carried out a geophysics survey, and they completely missed the fact that there is brackish water to salt water at 40 to 60 meters depth, which is well within the capability of the standard ERT method. Sorry, not ERT, the VES method that they claim to have used. And that's a really good example of the extremely variable quality of local contractors. They should have picked that up, and if they had, it would have saved constructing that borehole, and we'd have known from the beginning that it would be better to put in a shallow dug wells rather than an expensive borehole. And I arrived on the project after that had been done, and by then the borehole had already been drilled, and everybody was scratching their head and saying, we have salt water, what do we do now? And the ideal answer would be get a reliable geophysics survey, because in that example, there's no question when you're carrying out that water feature survey, a number of the surrounding boreholes had salt water, and you go, okay, there's a real risk here that we're going to have salt water, so we should carry out a geophysical method that has the ability to determine salt water at depth. We need to find out what that depth is, and then from that we're going to construct or not construct. And the answer would have been don't construct, I would imagine. So in the right context, and that was an example where a geophysical method definitely should have been carried out, and but you need a reliable answer, and if you haven't got a reliable supplier, you're not going to get that answer.
The desk study stage. So before going to site, how much would you think that would enhance the probability of a drill and see being successful?
So if it's a coal project where you don't have any on the ground information, it helps quite a lot. Again, expertise helps enormously. So I can discern from a topographic map an enormous amount of hydrogeological information, which I would then produce a hydrogeological map from. But if you're an engineer, you would normally go to the hydrogeological map, which doesn't normally exist in East Africa, and Africa in general. So that's where expertise is key, as always. But in an environment where you've got a local insight, and Ian is a great example of this, where you can then quiz him about different bits and pieces, and he thinks it's useless information, but actually invaluable is the actual answer. And you find out, oh, can we please go and carry out a water feature survey and find out from the nearby borehole suppliers, borehole owners, what's going on? And they say, oh, well, our well's not very good, it's got salt water. To go, that already has told you an enormous amount of information at your desk study stage. You can follow that up in your water feature survey, double check that those answers aren't just hearsay, and then carry out the geophysics and determine, well, yeah, borehole's not the answer here, because boreholes produce so much more water for much the same cost as a well. They're the preferred option. But if you've got salt water at depth, then the shallow solution is always the best way to go. So the dug well's the right answer there. And that's how it's turned out to be. in that example.
Mhm.
Is there anything you can do in that situation, like fill in half the borehole and just use the top off, or
Well,
is it just abandon
yeah,
and start again?
yeah, great question, Jonathan. So yes, we did that. Ideally, though, you would be putting liquid grout in, and that requires a certain amount of specialist equipment. So we were putting in packets of grout into the bottom of the well. But the problem with that is that they stay inside the casing and screen and don't get into the gravel pack around the edge. So that's why a liquid grout is a better option. In an ideal world, what you would do is you put liquid in, and then you would use the drilling rig with basically manufacture a piston with basically a steel plate, a bit of wood, and then some car tire, inner tire, which then forms a rubber seal against the side of the borehole, and then you just use the drilling rig to push that grout through the slots in the casing into the well on either side. It works to some degree. Ideally, if you didn't have the screen in there in the first place, it would definitely work. But with screen in, it may not work very well either. So the method we came up with was low cost solution, and it improved the well enormously, but it didn't solve the problem. Ultimately, one of the problems that you get with saltwater mixing with fresh water is you get quite a lot of water quality issues. So in your example, when the people of Israel came to Meribah and they found the bitter water, it's very common to get bitter water when you've got fresh water and saltwater mixing. It's to do with the sulfur chemistry. So are there any more questions? It's a bit worrying that I've silenced everybody.
Splendid design.
Well,
But I've used we used ERT and seismic resistivity tomography as well. You get a mixture of these to get rock head depth below a dam in Perthshire. So I've used it fairly recently in the UK, but I've never used anything like this in Africa. So.
No, exactly. And the seismic method is a fantastic method, but you need to have the right source to be able to operate it. And if you can't, and that's where the method falls down in Africa, because you then got to have essentially a trailer and weight system in order to get a reasonable.
how big is the weight?
Do you know, I've never seen it in operation, but so I imagine it's going to be of the order of 50 to 100 kilos, something like that, and it's winched up and then dropped. In fact, I think it's also accelerated as it's thrown onto a plate on the bottom of the fall. So it basically has to be considerably heavier than the sledgehammer in order to get that energy in.
Yes. And have you any idea how high it goes to drop?
Yeah, it has. I've seen a picture of the equipment. So it's got a small mast. So the mast is probably of the order of 4 or 5 meters, and then you just accelerate it from there and drop it. I mean, it would be feasible to if you've got some fabricators to do that in Africa. But then the issue then is how portable is it, and the amount of engineering time it takes to actually construct it and get it operating. But with a good bush engineer and a good bush fabricator, you could almost certainly produce something locally.
I would think so. I mean, what's going through my mind is I've had some fence posts driven, and it's a little attachment that goes on the front of a 3-ton excavator, and it pulls up a weight and just bangs it back down again. Now, that's not big enough for what we're talking about here, but it's the weight that would be might be 50 kilos.
So it's a question of how it compares with a sledgehammer. So a sledgehammer gives you 20 meters, so you're going to have something that's got probably 3 times the weight and force to get enough bang for your buck. And you probably want to go even larger than that, just because it's not going to be quite as efficient as you want it to be.
Yeah, but I could imagine something that was hauled up a bit of a rig and dropped. I don't know. You could maybe get 5 meters on some sort of improvised rig. But it's how you calibrate that to know, and because presumably the kit that you're talking about is kit with known parameters.
It is. So the way the seismograph works is it has a geophone, which basically is a trigger. So one specific one is a trigger, and it starts reading once the acceleration hits the ground,
Yes.
and then it'll continue for a period of time. So it doesn't. There's no connection between the source and the instrument. The instrument is operating independently,
Yes.
effectively. You basically trigger the source when you want to, and then it starts reading when it reacts to what you've done.
And so the magnitude of the source, it's measuring time. So actually the precise parameters of the source maybe aren't so important.
No, they're not. It's precisely the energy of the seismic wave. So you want to drop that weight and you want to feel the bounce under your feet.
Yeah.
Basically, I can remember working on a peat bog in Scotland in the Mull of Kintyre, where the drilling rig was using percussion, and every time they were operating the percussion bit, there were these waves flying across the peat because of its elasticity. And at one occasion we were getting meter waves and getting thrown off our feet, and I was concerned that we were going to lose our rig into the peat bog.
Yeah.
But yes, exactly so.
Mm-hmm.
70s, there were. Oh, I guess I'm unmuted now.
Yes.
Yep. In the 70s in Zambia, there were a number of percussion rigs drilling boreholes. It may be they're more widespread in East Africa, and if you could get one of those, the drop was quite considerable. And
yeah, no, it's a good thought. Yeah,
the weight was probably 10-foot length of 5 inches diameter steel.
Yeah,
2 or 3 weight.
No, it's great thought, Alan. Yes, you could certainly do that, especially if you filled it with some sands of gravel or something heavy, so that you just drop that onto a plate. That would work quite well, I would have thought.
It's solid steel.
Well, yeah. So the method I'm familiar with contains a shell which is basically solid steel on the outside, but it's hollow in the inside with a flap on the inside because you've got to be able to pull out the sands and gravels or whatever it is.
That's the baler, but the drilling is done by a piece of solid steel, 10 foot long, 5 inches diameter, and sharpened from time to time by heating it in a big fire and hammering the end until it's sharp.
So the chisel, yeah, okay, I'm with you.
That's a big percussion. I'm sure.
Indeed, so, and that may well be just what you need. So that course is a trailer system, so that would probably be good enough.
Well, if they're passing around, they may be just parked up, disused somewhere.
Indeed, so that would probably answer that question. So maybe the seismic method would work. And
that's about 300 kilos if those parameters are right.
Yeah.
Yes, which sounds like compared to say a 30-40 kilo sledgehammer, that sounds pretty promising, doesn't it?
Yes, doesn't it?
Yeah.
But again, you've got to get the percussive rig to site and
and to each site as well. But I mean, they're pretty mobile, because they basically, as where a Land Rover can go, they can go.
Yeah, trailer mounted, and had their own diesel engine.
And then the geophones, is that the expensive part of the toy?
Yeah, so basically your seismograph and your geophone array, that's the expensive bit. So the seismograph, because it's got quite a bit of processing it needs to do to identify the appropriate element. For engineering and groundwater purposes, they'll typically just focus on the refracted curve because it produces a straight line, whereas the reflected produces a curve, which means that the mathematics is quite a lot more complicated. So if you use refracted, then you've basically got to just do a fit to that light, those geode arrays. You know exactly where those geodes are using measurement, and then you should then get a straight line passing through there, and the software can pick that out and then give you your answer fairly.
The reason we were having the conversation about the thing providing the impulse was because of the practicalities or the impracticality of getting kit from the UK out there. So In other words, taking out something that's going to give us that impulse would be difficult and expensive, I think is what you're saying.
Yeah, it is what I'm saying, which is why Alan's comment is quite a good one. Is that if you were to take out the instrument from England or from the store, wherever it is, I mean, you might even have it locally, if Ian was storing it, for instance, then you would then in the survey setup you would obtain the appropriate source and then bring that in your hand luggage, because the seismic instrument will come in your hand luggage. It's not. The weight is not impossible. So in fact, pretty much all of these instruments you can carry in hand luggage, albeit with an extra weight allowance. The geophones themselves are quite small, and so they're sort of this sort of size with basically a steel pin on one end and lots of electrical windings on the top end, and they're amazingly robust. Actually, they're a really clever engineering toy.
Okay. So is the way forward with this for perhaps Jonathan to speak to the board and see whether this is something that would be worth taking forward?
So I think that the first discussion is to canvass the board and find out how important price reliability is, and what value they put on that, and what they feel that the donors put on that. Because if the donors and the board are comfortable with variations, then using local solutions is probably the best way forward. And that probably heads us in a direction of not using our own equipment. But we're engineers; we like to use our own equipment, so and do stuff ourselves. So it would be good to have local equipment, but I'm not 100% convinced that's the right answer. Just because once you've bought it, then you're then tied into doing at least 10 studies with that equipment, and that equipment may not be appropriate on all those studies. So what's that multiple? Maybe it's 20, 30 studies before it actually pays for itself. So I'm not sure it's the right answer, but it is an answer.
So I think the first question is, how many boreholes might we have liked to try and do a geophysical survey on in the last 5 years?
Yeah, exactly. I think you'd have a look back over the last 5-10 years, see how many studies we looked at, how many of those would have benefited from geophysics, and which kind of geophysics, and that would then head us to the right answer. My thinking is that in East Africa we'd probably be able to find the suppliers we need. In Kenya, I'm already aware of one in Ethiopia, and based on that was probably that I'm guessing that's going to be the right answer. But if we're doing studies outside of East Africa, so I don't include Zambia and Malawi and other places like that inside East Africa. So let's say you're down there, then yeah, so it's knowing who the reliable local suppliers may well be the better answer. It's definitely the better answer, but there's a learning curve required to reach that point.
If you've got somebody like the people you were working with Ian with, who gave you poor results, if you were to work alongside them, as in physically alongside them, and you could, is the equipment they had, is it usable?
So it's a question of how good they are at listening. Is an issue, and unfortunately, if most of these guys will know that they're not very good at what they're doing, and therefore that causes its own issues. So
that can be taken one of two ways. It could be a tremendous opportunity for them to improve themselves.
In an ideal world, absolutely right, Angus. So in Sierra Leone, they were wanting to charge us European prices, and were then wanting to double the price on us, and I doubt we'd have got a very good result anyway. So that circumstance, definitely, if you're in Sierra Leone or West Africa in general, then having your own equipment is the only way. So an environment that has a problem with corruption, that is really the only way to deal with it, because it basically takes away the leverage that they have. If you're in somewhere like Kenya or Ethiopia, then the local suppliers will almost certainly be more than good enough, and that is replicated in lots of different countries as you go south. But again, it's a question of knowing who's the good guy and who's the guy to pass on.
Yeah. Okay. All right.
Changing the subject.
Jonathan, is this something we should somehow come up with a plan to take forward, even if only to understand it's something we don't want to do?
I don't know, to be honest. I have to think about that. Yeah, I don't know. Partly it's about our attitude to risk. If we wanted certainty in the project and the project costs and so on, then that does, as Martin says, points you in the direction of doing lots and lots of ground investigative work beforehand, so as to minimise the risk. But we haven't been in that situation very much, have we?
I thought so.
So the other piece of this, Jonathan, I'd be more than happy to speak offline on the phone if you want to just run through the different bits. But the other part is where there's a water quality issue. So where you're close to salt water and brine, and there you definitely need to carry out a geophysics survey. So there are some circumstances where geophysics absolutely should be done, irrespective of the fact there's a significant cost attached to it. But in an area where there's unlikely to be, where it's likely to be fresh water, then it's a more measured answer.
Yeah.
Okay.
Not one size fits all, really.
No, it absolutely isn't, and unfortunately, there's multiple instruments. I mean, we could comfortably spend £200,000 on this, and to cover all the projects we need to. Which we're not going to do, but we could do that.
Drill a lot of 6-inch holes for that.
Indeed. Yeah, well, this is the point, isn't it? That's why I mentioned the elephant in the room, because it's one of those issues where if you've got a supplier who's a specialist, they get round this because they do a lot of it. But if you're only doing one or two, then you run, especially at our level where you're only doing one borehole at a time on a particular project, then you run into this elephant in the room.
Yes.
Going to the other extreme, have you ever had experience of using water divining?
So I know, yes. So on this topic, and of course geophysics is in the broader sense a form of water divining. So I've seen people doing it. I am a charismatic Christian. I believe there's a spiritual aspect to the way water divining works. It's not something that I want to encourage doing it for that reason. Having said that, there's also there is a how would I best describe this? So in most locations, when you drill, you will get water. I would say 90% of wells will hit water. So whichever place you pick, you've got a 90% chance of inverted commas success. So it's one of those reasons. So even if you don't get a twitch on your fingers, and then there's a good chance you're going to pick a place that works, and then you're going to think it's the right thing. There's in science and research, there's a specific confirmation bias was the word I was looking for. It's a classic confirmation bias solution. I think that's the jargon word for it, isn't it? So yeah, obviously I'm a skeptic, but I'm not a skeptic either. From an engineering point of view, I'm a skeptic, but from a spiritual point, absolutely not. And yeah, it was used for as the dark arts, literally, in the pre-Christian days. So
yeah.
if you want to know its roots, look no further.
And probably because the diviner wanted to keep business to himself or herself, she kept the secrets so that she could keep on earning money.
There you go. Yeah. So
It's typically what happens with when evil comes in.
no, indeed. So, but if you're in my part of the world, in the south and southeast, where we're on and near chalk, most of the time you'll drill and get water. And even if you're on the tertiary sands and gravels, as we are in Southampton, you will get layers that are more than sufficient for wells, and they will have a pretty good productivity, certainly at a one household level. If you're trying to irrigate your farmland from your wells here locally, that doesn't work so well. But if you're in the chalk, obviously it does. So if you're in the right rock type, you'll get it every time. If you're in the wrong rock type, sometimes, and if you're in the very wrong rock type, you'll only get a poor productivity. So taking Scotland as an example, you're typically on hard rock, and there you'll get a low yield most of the time, but sometimes you'll be dry. So maybe I'm just a skeptic because I just live in an area where we don't really need a hydrogeologist, you just need an engineer.
That's been very helpful.
Yeah, that's interesting. It's filled in some of the blanks. In terms of awareness, we're aware of techniques and the process. And so thank you very much for that.
You're welcome, Angus. And there, although there are lots of variations within each group that I showed you, that you now know the main parameters that can be measured and what they can tell you and where they're strong and where they're weak. Yeah. So hopefully that's more than enough to point you in the right direction.
Okay, well, if there aren't any other questions, then I think we'll wrap it up and just, as we say, thank you very much, Malcolm. Again, I know there's a tremendous amount of work that's gone into this, and a well presented talk. It looks relatively easy, but there's a lot of time goes into it. Yes. So thank you very much, and I really appreciate our sort of little group of 3 talks, taking us through a process, hopefully leading to water supplies. So we look forward to your next talk, which is in 2 months' time.
It is indeed.
And our next talk, I've got a chart on the wall here, excuse me while I lean over. So 6th of May, we're looking at solar power. And then 3rd of June, Malcolm is back with well design and construction. So that's what's on the cards next.
I won't miss that one.
6th of May and 3rd of June. So what was that, Jonathan?
I'll make sure I don't miss that one.
Yes, yes.
What, the 3rd of June?
Yes.
Or the 6th of May?
Oh, the June one, yeah. Well, both actually, yeah.
Okay.
Great. Yeah, thanks very much.
And thanks everyone else for attending. Okay. Good night, everybody. Good night.